Hi, my name is Vincent, and today I'm going to talk about the second topic, which is the motion of falling object, at the second lab. And in this presentation, I'll talk about the purpose of this lab, the models and fundamental principles, and then I'll talk about the steps inside the experiment, and then compare and plot these computational models and answer some further questions. So the purpose of this lab is to do experiment and observe the position of an object after being dropped from a height, and then we'll compare the measured data with two other computational models. This experiment will demonstrate the principles of Newton's second law, gravitational force and drag force. So the Newton's second law states that at any instant time, the net force on the body is equivalent to the rate at which the body's momentum. And in this particular situation, the total net force will equals to the drag force plus the gravity force. The gravitational force will equals to minus m multiplied by g hat, and the drag force will equals to minus b multiplied by the velocity, the magnitude velocity square multiplied by v hat. So the brief preview of the main result of the lab is that the red line represents the experimental model, and the yellow line represents the computational model with drag force, and the blue line represents the computational model with no drag force. Overall, you can see that the yellow line with the drag force keep it close to the experimental line more than the blue line. So the steps inside the experiment is I'm going to record the video of the paper ball falling from the particular height, and then I'll use tracker to track the paper ball position over the set time period, and later I'll use GlowScript to create a model of the ball predicted motion. This is the video of my experiment of the ball falling. Overall, you can see that on the left hand there's a time interval, and then there's the y updated axis, and you can see that as the time goes, the graph represents like the y is falling down. So I'll use some codes in GlowScript to to put in the data with a drag. Is that when the b equals to 0, the b constant, the model is gravity only, and there's no air resistance. So the total net is equals to minus ball mass multiplied by g hat, and the ball vector is updated every time difference, which is 1 divided by 30, and the ball position is updated every time difference. And this is my GlowScript data code with drag. In this section, I'll put the b constant as 0.003, and then I'll include this drag force by the equation like minus b multiplied by the magnitude of ball velocity squared multiplied by the norm of ball vector, and then the net force will equals to the total of drag force multiplied by the gravitational force. So this is the model. So I'll talk about this model a little bit. So as you can see that the experimental model is the red line. It is close to the computational model with drag force, and the blue line represents without drag force falls like faster because there is no drag force, there is no air resistance in this. So because the setting is the earth, so there are air resistant inside the ball, and this indicates that my graph has successfully indicated there's no large discrepancy in the later time interval between the experimental and the computational model with drag force, but there's a large discrepancy between this experimental model and the one without drag force. So the errors that may possibly happen to a little bit of discrepancy in models is maybe two numerical errors, or maybe error identifying the center of mass inside the tracker. So I'll answer some further questions. So what does it mean like terminal velocity is the drag on the ball is going to be equal to the net force of the gravity on that ball. So the net force on that ball must be equal to 0, and the ball has no acceleration. So the drag is indeed a very crucial component of the terminal velocity, and therefore the model, like on your left hand, the model have to take into account which depicts a terminal velocity. Like what if the object was thrown downward? The end velocity would remain the same, and looking at the models on your left hand, you can see that the drag and the mass of the object is very important. Like tossing it downward would cause it to slow down until it achieved the same terminal velocity. So my name is Vincent. Thank you a lot for your listening to my presentation. I hope to see you guys in later labs. Thank you.